All right, today we're going to talk about section 5.3 on the first derivative and critical values. Now, since this is our first section of chapter 5, just as a quick overview, what we're going to be talking about for chapter 5 is we're going to take the things we've learned, like derivatives and limits, and talk about how they can help us draw graphs. So derivatives, mainly derivatives, but also a little bit of limits, can be really, really helpful when it comes to graphing, and that's what we're going to focus on in chapter 5. So let's start with some vocab today. The first two, I'll put them up together. If you're talking about the absolute maximum or the absolute minimum of a function, it's pretty straightforward. Maximum means biggest, minimum means smallest, and absolute means absolute. So absolute maximum means the very biggest value that f of x ever reaches. Or if you're thinking about the graph, it's the highest point it ever reaches. And the absolute minimum would be the lowest. Now, these two words together are called extreme values, or sometimes they're called extrema. So if you ever see, if you see a homework question that says, find the extrema, it's asking you to find both the absolute maximum and absolute minimum. Now, as for a quick sketch here to show you what I'm talking about here, let's say we have a function that looks like this. The one point that's jumping out at me would be this one right here. That's the absolute minimum. That is the lowest point that that graph ever reaches. There are no points on the graph that are farther down below that one. Now, as for an absolute maximum, this graph doesn't have one. If you have, this graph actually has an arrow on both sides, but if you have even one arrow pointing up like that, meaning going up forever, then the graph doesn't have a highest value. It keeps going up forever. And in fact, you could have a graph like this that has no minimum or maximum. This graph has no absolute minimum or maximum because, number one, no maximum because it's just going to keep going up forever, keep getting bigger and bigger. And number two, no minimum because it's just going to keep getting smaller and smaller on the other side. But what you see on the blue graph there, that red point that I marked, that would be an absolute minimum because it's the very lowest point that that graph ever reaches. Okay, we also have two more types, or one more type of minimum and maximum. That's very important. I'll put them both up together again. There's two names for them. They actually mean the same thing. You can call them a local minimum or maximum, or you could call a relative minimum or maximum. And what I said is a local maximum is when it's a point that's bigger than everything, and I put it in quotes, I said near it, and I'll show you what that means in just a second. And same thing for a local or relative minimum. It's smaller than all the values of f of x that are, again, kind of, quote, near it. So let's look at that same picture I just drew. We had a graph that looked kind of like this. And I said, okay, well, this graph, this point right here, is the absolute minimum. But what about this point right here, that purple point there? It's definitely not the absolute minimum. There are points on the graph lower than it, like the red one. But this is what we mean by near it. If you take that point and draw a circle around it, and just look inside that circle only. So let me redraw the circle. I'll make it bigger too. Here's that green circle, and inside it, the graph just does this. And the purple point was right there. Now, if you look in that green circle, that's the minimum. I mean, that is the smallest point in the green circle. So that's what we call a local minimum or a relative minimum. Local means in one specific spot, or relative means compared to the points just to the left and right of it. So that green circle, that purple point in the green circle, is a local minimum. And this yellow point right here, for the same reason, is a local maximum. It's not the absolute maximum because there are points on either side of it that are bigger than it. That's what those arrows on the end mean. It's definitely not the absolute maximum. There are bigger values on the graph. There are higher values on the graph. But again, if I draw a circle around it and just look inside the circle, this time in that little circle, what I see is something like this. And the yellow point is the maximum there. So a good way to think of it, if you have a graph that looks something like this, let's say it kind of goes up and down, and it kind of keeps switching up and down like this. Think of it as like peaks and valleys. Every top point here, 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 and here, those are all relative maximums. And every valley or every low point, here, 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 and here, is a relative minimum. So as a graph from left to right kind of goes up and down and twists and turns, every peak is a local maximum and every valley is a local minimum. And the highest one of each one could be the absolute maximum, as long as, again, you don't have the arrow on the end. This graph I drew at the end, it's another example of one that does not have an absolute minimum or maximum, because on one end it goes up forever, and on the other end, down forever. All right, so this is what we're going to spend the next few days focusing on, but for today, we're going to focus on one thing. Critical numbers, or sometimes called critical values. Now, a critical number is going to be the first step in finding all of those relative minimums and maximums. So what I want to do for today, for part one, just focus entirely on finding critical numbers. And then for part two, we'll talk about how to use them to find the minimums and maximums. So a critical number is basically anywhere, if you take the derivative, this is where derivatives come in. If you take the derivative of the function f prime, any number that makes that derivative either equal 0 or become undefined, that number is what we call a critical number. So like if I have f prime of x and I plug in 5 for x, and the answer is either 0 or undefined, then that number 5 is what we call a critical number. And that's what we're going to focus on today, is how to find those numbers. So here's how to do that. If you have a function f of x, or I'll just call it f, and you want to find its critical numbers, step one is to find the derivative, because this is all about derivatives. So you take a little bit of time, you think about all that chapter 4 stuff we learned, power rule, product rule, whatever you need to do, chain rule, and you find f prime of x. Now in 2 different steps, we are going to, number 1, figure out values where it equals 0. Now the way you do that is by setting it equal to 0 and solve. So as soon as you find that derivative f prime, the first thing you do, just set it equal to 0 and solve for x. Whatever answers you get are critical numbers. Now the other part's a little bit trickier. You basically just kind of have to ask yourself, what would make this thing be undefined? And really what we're looking at right now is, if you see a rational function, a fraction, like x plus 5 over x minus 7, wherever that denominator ends up equaling 0, that's where it's undefined. So you're going to set the denominator equal to 0 and solve to find those undefined values. So let's go ahead and try one out. I want you guys to see how this works. Here's our first example for today. Our function is f of x equals x squared over x plus 1, and we want to find the critical numbers. So step 1, find f prime of x, always. Now this one is going to be quotient rule. We definitely have a rational function. We have x squared on top, x plus 1, that's function of x on top, function of x on bottom. There aren't really any shortcuts here. If you remember back to your quotient rule notes, sometimes you can get around quotient rule, but not for this one. So let's just go ahead and do quotient rule. Quotient rule says, first you square the bottom, and then you do on top, you do the derivative of the top, which would be 2x, that's a power rule, times the bottom, which is x plus 1, minus the derivative of the bottom is actually just 1. And remember, I did it separately. The derivative of x is 1, The derivative of 1 is 0, so the derivative of x plus 1 just ends up being 1. And then that's times the top, which is x squared. So let's clean this one up a little bit. If I distribute the 2x here, I get 2x squared plus 2x, and then I get minus x squared, and it's still over x plus 1 squared. And if we combine our like terms, 2x squared minus x squared would be x squared plus 2x over x plus 1 squared. So that's just finding the derivative. That's chapter 4 right there. That was just quotient rule, how to find the derivative. Now, to find critical values, remember we're kind of thinking two things. Number one, what would make this equal to 0? And number two, what would make it undefined? Now, when you get a rational function like this, a fraction, it makes it very simple, actually. What you do in 2 steps, in step 1, just take the top, set it equal to 0 and solve. That's going to tell you where this function equals 0. Because remember, when you're talking about a fraction, if the top equals 0, we don't really care what's on the bottom, because 0 over any number is going to equal 0. So if you set the top equal to 0, that shows you the function equals 0. And if you set the bottom equal to 0, so 2, that'll show you where this thing is undefined. So if I solve the dark blue and the green equation there, I've basically found all my critical values. So to solve the dark blue one, I would factor out x. That gives me x times x plus 2 equals 0, which gives me x equals 0 for the x I factored out, and negative 2 from the x plus 2. Now the green one, I don't even have to do any work. It's ready to solve. If x plus 1 squared equals 0, it's already factored and equal to 0, I get x equals negative 1. And again, that's just the shortcut trick you probably learned back in Math 3. When you have the factors, like on the blue one, when you have the x plus 2, the answer is negative 2. You change the sign. On the green one, when you have the x plus 1, the answer is negative 1. So basically, my final answer is all 3 of those things together. It's 0, negative 2, and negative 1. Those are your critical values for that. Now that's as far as we're going for today. In part 2, we'll talk about how we can use those numbers to find the local minimums and maximums. But that's part 2. We'll stop there for today. I do want to do one more example with you guys just to make sure you really get this. So let's find the critical numbers of this function right here. We have f of x equals x to the 3/5 power times 4 minus x. Now, if you take the derivative the way it's written, it would be product rule. But remember, sometimes you can avoid product rule, and I would probably do that here. So what I would do first is distribute the x to the 3/5. And I would say f of x equals 4x to the 3/5 minus, and then you're going to have x to the, now remember, when you're multiplying x's, you're adding the exponents. That x is x to the 1st power. So what you're doing is you're doing 3/5 plus 1. And 3/5 plus 1 would be 5 over 5. So 3/5 plus 1 is going to end up being 8 over 5. Now remember, that's not the derivative, that's just simplifying the problem to make taking the derivative easier. To find the derivative now I'm going to do f prime. Now instead of having to do product rule, I can just do power rule twice. So for the first one, I multiplied by the exponent. 3/5 times 4 would be 12 over 5. And then I subtract 1 from the exponent. 3/5 minus 1, or 3/5 minus 5 over 5, would be negative 2/5. Now for the second one, it's a little bit easier. Leave the minus. You multiply by 8/5, and then you subtract 1. We'll leave the x. Subtract 1. 8 over 5 minus 5 over 5 would give me 3 over 5. So that's the derivative. I avoided product rule by distributing first. It was a little bit messy because of those fraction exponents, so just be careful there. But it was just power rule twice. Now, we have our derivative. The next step is to set it equal to 0 and solve. Now, there was a trick I showed you in first semester where I said when you have exponents, you can always factor out the lower one. I said it's trickier when you have negatives and fractions like this problem, but it's an important trick to know because I was thinking of right now. So back then I said right now it's just kind of simplifying, you don't really have to do it, but I think I even told you, I said eventually we're going to get to the point where we're taking these derivatives, we're setting them equal to 0 and solving, and that's the only way to do it. And that's what we're doing right now. So let's do that. Let me start. I'm going to take this, let me just recopy it. Set it equal to 0. Now you're looking at that and you're thinking, that looks like a mess. I have a -2/5 exponent, I have a 3/5 exponent. Well, what you want to do is factor out the lower one. In this case, it's x to the -2/5. Now when you do that, it'll leave the 12/5, and that's it. Because I had an x to the -2/5, I factored it out, it's gone. On the second part, we'll leave the 8/5, and here's where I said it always kind of works out nicely. What you have when you're factoring out a variable, you're subtracting the exponents. So if I start with x to the 3/5 and I factor out -2/5, my exponent ends up being 3/5 minus -2/5. That's what I'm doing. I'm starting with the 3/5 power. I am dividing out -2/5 or subtracting it. Now see, when you subtract a negative, you get a plus. When you add it up, you get 5/5, which is actually just 1. So what you get here is just x. And that's why I showed you that trick first semester. I said it wasn't a big deal back then, it was just simplifying, but it is a big deal right now. That's the only way to solve this question, is to know how to factor out that x to the -2/5. Now once it's factored, I'm going to erase this, to use this space here, erase the green. Okay. Once it's factored, you can separate and solve. So either x to the -2/5 equals 0, or what was inside the parentheses, 12/5 minus 8/5 x equals 0. Now if you solve those two equations, you've got your critical values. Now you don't have to worry about undefined here. The undefined, it's not a fraction, it's not something over another. When it comes out just like one single thing, just don't worry about undefined. Set it equal to 0 and solve, and that'll give you all your critical values. So my first critical value is just x equals 0. If x to any power equals 0, then x equals 0. Now the second one, one thing I might do to kind of clean up the second one is if you just multiply everything by 5, it'll basically just cancel out those exponents, or the denominators. So basically you'll have 12 minus 8x equals 0, because 0 divided by, or if you're multiplying by 5, 0 times 5 is still 0. So if you add 8x to both sides, you would have 12 equals 8x. Divide by 8x, and your other critical number is reduced by 4, and you get 3/2. Let's write it down here. So your final answer to that question is those two things together. It's x equals 0 and 3/2. So that's two examples for you guys of how to find critical numbers. It's find the derivative first, f prime, set it equal to 0 and solve. If it's a rational function, set the bottom equal to 0 and solve. We didn't have to do that on the second example. But just remember, the reason I gave you this second example, I wanted to remind you guys of this trick right here. When you have a common term, you can always factor out the lower one. Even if it's negative, even if it's a fraction, you can always factor out the lower one. Other than that, that's what we're doing today. We're going to find critical numbers and stop, and then as I mentioned earlier in part 2, we'll talk about how to use those critical numbers to find minimums and maximums.